participants, welcome to the talk on tailoring nanoscale systems by bottom-up design, atom by atom, by Professor Wiesendanger. So, Professor Roland is a university professor for experimental physics at University of Hamburg, Germany. In 1987, he completed his PhD in experimental physics at University of Basel with summa cum laude. And in 1990, he completed his habilitation in experimental physics at University of Basel. Shortly after that, he joined as private lecturer at the same university. And after that, he joined in 1993 as a full professor at University of Hamburg. Since then, he has been appointed in various higher positions. So in 2003, he was appointed as vice dean of Department of Physics at Hamburg University. And from 2003 to 2012, he was the managing director at Institute of Applied Physics there. He has published more than 650 publications, including research articles, review papers, and book chapters. Moreover, he has been author of 2 textbooks, editor, co-editor of 9 books and 8 conference proceedings. Also, he has been invited for 600 talks at international conferences, universities, and research institutes. He was the first scientist in Europe to receive the advance grant of European Research Council for 3 times. And he has received numerous prizes and awards. Recently, in 2019, he was awarded the honorary Medal de Scientia at Humanitate Optima Meritis by the Czech Academy of Sciences in Prague for his scientific merits and pioneering work in the field of spin-resolving scanning tunneling microscopy and magnetic phenomena on the atomic scale. I gladly welcome Professor Roland today to share with us his pioneering work in scanning tunneling microscopy-based single atomic manipulation techniques and how it is used to construct nanoscale systems with atomic level precision for quantum designer physics. Finally, I would like the participants to post your questions in the Q&A box below. Please use that instead of the chat box. So, Professor Roland, I would like to take up the webinar and take up the platform and start the webinar. Thank you.
Yeah, thank you. Hello, good afternoon. First of all, let me thank for a very kind introduction and also for the kind invitation to this colloquium. It's a great pleasure for me today to introduce a very exciting topic as far as I believe, namely the tailoring of nanoscale systems from the bottom up, atom by atom. So I understand that you have a lot of different background in your studies. So let me start just by explaining a little bit what you see here on the first slide. It's actually an atomic scale device where we have arranged individual atoms here, one by one here, to construct a transport device. So we are measuring then current through this atomic scale structure here between these 2 gate electrodes. And the individual bright spots, as I said, are really the individual atoms. And so I would like to introduce in this talk first methods which can actually visualize such atomic scale structures, which allow to build up such structures on the atomic scale, and how we can make use of that for future applications in electronics, but also in memory and logic devices. So let me start by a more general background of what I'm going to talk about. So you can describe this as quantum designer physics, and that's the overall goal currently, not only of our group, but many groups worldwide. And the background is that this quantum designer physics relies on the possibility of a bottom-up fabrication of artificial material systems, not just systems which you can synthesize, say, in a chemistry lab, but really from the bottom up, you can design structures which would not be possible to achieve, say, by chemical methods or, say, by self-assembly. Moreover, in the field of quantum optics, we have cold atom systems. Some of you might work in that area, and you might know that there are quantum simulators possible, which allow to simulate the properties of quantum systems. And then we have, of course, the theoretical tools, toy models to describe very simple physical systems, and especially the interaction of theory of quantum simulation and this bottom-up construction gives us really novel perspectives for quantum technologies. And this is, of course, a very exciting research area because future electronic devices and future spintronic devices will, of course, rely a lot on quantum effects. So I would like to give you a little bit more insight, especially in this area here of bottom-up constructed material systems. So what are we going to do here? Basically, we start from individual atoms, and you know we have a free choice from the periodic table. But it's not just the properties of the individual atoms as we know from the gas phase, but we can tune these properties now by bringing them on some substrates. Substrates which we can also freely choose from the periodic table. And then we basically have hybrid systems of individual atoms on surfaces. And their properties are very much different from the properties of atoms in the gas phase. And so we need new tools, as you will see, to do single atom spectroscopy to really probe the properties of individual atoms on surfaces, to get information about the electronic states of such atoms, but also magnetic states with single atom magnetometry. I'm going to explain this in more detail later on. And then the nice possibility is that we can then use single atom manipulation techniques. So we can really play around with atoms on surfaces, as you will see in this talk, and we can construct artificial nanostructures, tailored materials and novel kind of devices on the atomic scale. And while constructing these nanostructures, we can online monitor the properties of the resulting structures, as you will see later on. Sorry, is there any problem with?
Sorry, Prof, please continue.
Okay. So, and while constructing these artificial nanostructures, actually, we can make use of distance-dependent interactions. So, of course, we atoms on the surfaces have some interactions, electronic interactions, magnetic interactions, and by tuning the distances between the atoms, we can tune the properties of these nanostructures. We can even tune the dynamic properties, as you will see in the second part of my talk, and so-called correlation effects can be tuned, which become very strong in low-dimensional systems, say 2- or 1-dimensional systems. And so all this leads to novel possibilities for materials which are artificially constructed by design, and you will see that we can basically get novel kind of tailored magnets or tailored superconductors or hybrid systems. So this is the general background. Now, how can we do all this? What kind of methods do we need in order to go along this direction? And so I will now first introduce wonderful method of scanning tunneling microscopy. And here you see the two pioneers, Gerd Binnig and Heinrich Rohrer, who have developed this technique in the early 80s at the IBM Zurich Research Lab. And this scanning tunneling microscopy technique actually combines three important concepts. The concept of scanning to get spatially resolved information, the concept of vacuum tunneling, and the concept of point probing. And by combining these three basic methods, they could actually arrive at a microscopy technique which allows to probe surface structures, as you can see here at the example of the famous silicon 111 surface here. And you see in these line traces here the signatures of individual bumps, and they represent actually the individual atoms. And that was a very early data set here published in '83. This was the time when I had to decide about my research theme, and I really got fascinated by these first results of Gerd Binnig and Heini Rohrer. So let me first introduce how we can get these kind of images of atomic scale structures. So I will show you a short animation how this technique works. This is shown here. You basically have an atomically sharp probe tip ending in a single atom, and you bring it very close to a surface so that you have a tunneling current flowing between the tip and the surface. And then you can use this tunneling current to basically regulate the distance between the tip and the surface while scanning. And so you can then get line traces which correspond exactly to the distances which you scan here. So the magnification is just coming along because the very tiny distances you scan with your tip are actually magnified to the macroscopic screen here of your computer. And then you can basically also translate the height information here of these line traces to a grayscale image here. And then you see much better, very nice atomic scale structures, usually some periodic patterns here, of course, also with some atomic scale defect, which you can recognize here. And so you get a very nice impression of the atomic scale structure, here in this case of a silicon surface. And you can do this simultaneously, of course, with many other kind of material systems, also compounds, say indium arsenide. It's also a famous semiconductor, and you can cleave these crystals, and then you can resolve the atomic scale structure, and you immediately recognize here two different atomic species. One atomic species which actually appears very bright, and then another species which appears less bright here, and this makes up this surface of this compound semiconductor. Or you can even image curved surfaces. So you might have heard about carbon nanotubes. They are made up exclusively of carbon atoms. Basically, they are rolled up sheets of carbon, like in graphite. In graphite, you have, of course, two-dimensional sheets, but if you roll individual sheets up, you can get such carbon nanotubes. And even for these carbon nanotubes, you can see the atomic scale structure on this curved surface of such a nanotube. And so the STM technique has been applied in many, many different directions here, right from the early days of the 80s, 90s of the previous century, and the technique has very much advanced. Now, how can we do these kind of measurements? Here you see in more detail what we are doing. I just said that we have an atomically sharp probe tip, which is approached to a sample surface, and we then record a tunneling current flow between the tip and the surface. So this current, which is typically on the order of nanoamps, is amplified by some amplifier, and then used basically to regulate the distance between the tip and the sample. So we have some feedback loop for that. And we have, of course, also a raster scan generator, which allows to scan the tip over the surface. And this motion is actually achieved by some piezoelectric material. When you apply voltages to this material, you can elongate or extend such tubes, and this gives us the possibility for three-dimensional positioning of these atomic scale probes. And in the end, the tip and sample is built in a microscope. Here you see the tip from the bottom, and here the sample inside the microscope, which is home-built in this case. So we usually operate home-built microscopes. They are built up by students, of course, with the help of a mechanical workshop. And then these microscopes are built in an ultra-high vacuum system, which provides very good vacuum conditions, typically on the order of 10 to minus 11 millibar. So this is comparable to outer space. And then we usually have cryostats going to very low temperatures, for instance, 300 millikelvin. This is very close to the absolute zero temperature. And it's even lower than basically the Big Bang background radiation, which you have in space. And we have very high fields available, up to 12 or 14 Tesla. So these are much higher fields than you are used to, for instance, in magnetic resonance tomography magnets. So it's a quite advanced technology which we are using here to probe these properties of individual atoms on surfaces. Now, of course, when I started to be involved in this kind of technology, a big question came up, and this is it possible also to combine this atomic resolution information with some kind of magnetic sensitivity? And this is the next big step which I would like to introduce here. You can imagine, as I said, the STM, the scanning tunneling microscope, was invented by Gerd Binnig and Heinrich Rohrer at IBM Zurich, and IBM at that time was heavily involved in magnetic data storage and hard disk drive developments. And so it was really an urgent question whether this technique can be made magnetically sensitive. And this was the topic I have chosen right from the early days of my research career. In fact, in 1990, I published the first successful experiments in this direction. So what did I do in order to make this technique magnetically sensitive? Basically, the trick is to functionalize these atomic scale probe tips by some kind of magnetic atom or magnetic cluster at the very end of the tip, so that you have a preferred orientation of your magnetic moment. It's like a magnetic needle which has a direction which is preferred here in space. And with that, you can really probe magnetic structures on surfaces because you can then make use really of the spin degree of freedom of these tunneling electrons. And to explain this a little bit in more detail, I again brought here a presentation, an animation which allows to explain this a little bit in more detail. What you can see here is a schematic of a very nice test structure which nature provides. It's a so-called antiferromagnetic structure. That means we have two different atomic sublattices indicated here in red and in green. So for the red sublattice, you have your magnetic moments oriented this way, and for the green sublattice, you have your magnetic moments oriented antiparallel. So this is called an antiferromagnetic material. And since I depicted here a structure in 2 dimensions, it's actually exactly representing what we get if we deposit a single atomic layer of manganese on a tungsten 110 surface. So this structure can be achieved by just depositing a single atomic layer of manganese. And what we do then is we basically prepare a magnetically sensitive probe tip with a very well-defined spin orientation at the front atom. And then after approaching this tip, we basically measure the flow of spin polarized electrons. That is, the electrons have then a certain spin degree of freedom, and the flow of spin polarized electrons basically depends then whether the magnetic moments of the tip atom and the surface atom are aligned parallel, as in this case, or antiparallel, as in this case. And since the two currents are different, it will then lead to a different distance of the tip when scanning at a constant current. So the constant current is kept by the feedback loop, and this means that the tip has to go up and down, but not with the periodicity of the atomic structure, but with the periodicity now of the magnetic structure. So you get basically an image now of the two different sublattices. You see the red spin sublattice here elevated, and the green sublattice here gives the dark rose. And so this shows basically the simulated image, what you would expect for such a surface. And from the right-hand side, you see now the raw data from the experiment coming in. So you see that we are really sensitive to these two different spin sublattices. Now, in this case, you see such a row-wise structure. Of course, if you have a surface with a different symmetry, not a two-fold, but a four-fold symmetry, then you can also see other kind of lattices as shown in the next image, which I present here. So this is a larger scan here of about 50 nanometers times 50 nanometers, and you can recognize here an atomic scale pattern. This is not the atomic structure, but it's the magnetic structure, in this case, of an individual iron monolayer, again on a tungsten substrate. And interestingly, also this iron monolayer exhibits an antiferromagnetic state, in contrast what one would expect from iron, because iron usually, as you know, is a prototype ferromagnet. But if you deposit only a single layer, we found, and this is one of the first discoveries we made, is that we basically have an antiferromagnetic structure. And you see that this antiferromagnetic structure can be imaged in the presence of all kinds of impurities. These are typically individual atomic scale impurities, or individual atoms or clusters on the surface, or even islands of a second layer here, which we deposited. And we can then make scans, each 50 nanometers times 50 nanometers in size, and then do a flight simulation over such a surface here. We did this basically for hundreds of images. You can really then get nicely atomically resolved images over large areas, and you see the spatial coherence of this magnetic lattice beautifully. You see the landscapes. This is just an atomic step here, but of course magnified with our microscope. And so you really have access to this atomic scale world. So it's fantastic. You can do this with atomic scale structure. You can do this with magnetic structures. You can probe electronic properties. And this is the technique which is really needed to enter this atomic scale world. Now, we have also introduced other methods to reveal magnetic structures on the atomic level. And a second technique is actually based on force microscopy, where we again have an atomically sharp probe tip, but in this case mounted at the end of a cantilever beam here. And in this case, we are measuring forces by looking at the deflection of this cantilever when we have basically force interactions between a probe tip and a surface. The advantage is that you always have a force interaction between a tip and a surface, no matter if it is a conducting, electrically conducting, or insulating surface. So, for instance, if you have insulators, or in this case, antiferromagnetic insulators like nickel oxide, you cannot reveal the atomic or magnetic structure with a scanning Tailoring microscope, but you need this kind of force microscope. And actually, we were the first to make, again, the tips of these force microscopes magnetically sensitive, such that we could reveal the atomic level structure of antiferromagnetic oxides. And here, I again show you an animation how this technique works. To get high sensitivity, we vibrate basically this cantilever beam to get higher sensitivity, and then we probe the atomic scale structure here of this antiferromagnetic oxide, the nickel oxide surface, by this atomically sharp probe tip. And again, you do this line by line, and again, then you can translate this line pattern into a color-coded map here, and you see beautifully the atomic scale magnetic structure of this antiferromagnetic oxide. Here you see the Fourier transform of the raw data set, and in the Fourier transform, you see spots here in Fourier space, in reciprocal space, which correspond to the atomic scale structure, but you also see two spots at smaller q vectors, k vectors, which refer to a larger periodicity in real space, and this is the superperiodicity, which is due to the antiferromagnetic ordering. So it was the first time that really these magnetic structures, both for electrically conducting as well as insulating surfaces here, could be revealed. And now the next step was, and that was the third invention we made, which was necessary for all the things I'm going to tell you next, is the technique of single atom magnetometry. So we cannot only resolve these magnetic structures on the atomic scale, but we can quantitatively probe magnetic properties and also electric properties of individual atoms on surfaces. So assume that we have here some atoms here in pink color, which are magnetic on an otherwise non-magnetic substrate. So how can we probe now the magnetic properties of an individual atom? Basically, we park then this atomically sharp probe tip just above such an atom. It's only a few angstroms between the tip and the surface atom. And then basically what we have to do, as we just learned, to probe the magnetic properties, of course, we have to make use of a spin-sensitive probe tip and then probing the magnetic state of the atom. And this magnetic state can be influenced by an external magnetic field. So we vary an external magnetic field and change basically the magnetization direction of these atoms and probe this with the atomic sharp probe tip. So to explain this in more detail here, once again, we have our atomically sharp probe tip with a very well-defined orientation of magnetic moment at the front atom. And if we have a magnetic impurity on a surface, usually this magnetic moment will rapidly fluctuate, as you see here. And so on a time average, we will just measure a conductance here, which would be equivalent as if we would not have a magnetic atom. However, it's clear when we apply a very strong external magnetic field, which allows to orientate the magnetic moment of this atom, say in this direction, then we have an antiparallel orientation, in this case, of magnetic moments of tip atom and surface atom, and this reduces the current, as we just learned. So we get a lower conductance. On the other hand, if we change the magnetic field orientation, we can polarize this magnetic atom in a different direction here. And now we have the same orientation of magnetic moments of tip atom and surface atom, and this increases the conductance as shown here. And now for intermediate field values, we still have some fluctuations, but still some preferred orientation along the external field orientation. So we will get some conductance values in between, and in the end, what we expect is a typical magnetization curve as shown here. And we did this actually for the first time for individual cobalt atoms on a platinum substrate that was reported in 2008 here. And here you can see for a different case of iron atoms on a copper surface, exactly this measurement of the conductance here in this magnetic tunnel junction as a function of the external applied field given in Tesla. And you see beautifully such a magnetization curve. And you can then fit these magnetization curves. So for those of you who know a little bit about magnetism, magnetization can be described by a Langevin function, and that includes the angle theta between the orientation of the magnetic moment and the surface normal. And it also includes an energy function divided by the thermal energy scale given by the Boltzmann factor times temperature. And the energy function basically includes two terms: the interaction of a magnetic moment with the external magnetic field B, and the term which basically describes the magnetic anisotropy. This is the energy related with a preferred orientation of your magnetic moment. And you can just fit the data here and extract the magnetic moment and the magnetic anisotropy quantitatively. So even if you just forget about the math here, it's important for you to know that we can determine decisive magnetic properties of individual atoms for the first time. And this is extremely important for the following. Everything can be extracted from experiment. In principle, you don't need any kind of formula. What we are going to do is we just measure now such magnetization curves, not only on individual atoms, but also on pairs or, say, more complex nanostructures. And this is what I'm going to show you here. Here you see pairs of individual magnetic atoms. These are cobalt atoms on a platinum substrate. And we have changed the distance here from 1.21 nanometer all the way down to 0.74 nanometer. This is 7.4 angstroms. You see the change in distance between the atoms already in the topography image of the STM. And now the interesting point is, if we measure the magnetization curves on these atoms, then we see that for this distance, the magnetization curves of the two atoms appear basically the same. Also for this pair here at this distance, the magnetization curves basically look the same. Actually, the standard magnetization curve as you have seen for the individual atoms. However, interestingly, in this distance regime here, if we then probe the magnetization curves, we see a very strange behavior here for this atom here on the left-hand side. Basically, we see when we increase the magnetic field, we decrease the conductance. And this is an unusual behavior which can only be explained by the fact that for those atoms here, in these pairs, we have an antiparallel orientation of magnetic moments. That means we have an antiferromagnetic coupling here, whereas the magnetic moments of these atoms here in these pairs are parallel oriented. Now, this is an interpretation, and you might ask, where's the proof? The proof can be given just by doing now spin polarized scaling tunneling microscopy. So you add the spin resolution for your imaging, and then you can directly see in a color-coded fashion of the measured spin resolved conductance that indeed you get a very different signal here for the pairs with the antiparallel alignment of the magnetic moment. So you can directly see it while doing these measurements. You do not even need any kind of sophisticated theory or formula. You can do this all on an experimental basis. So that's nice. And of course, you cannot only look for the coupling between two atoms, but next we have looked at the coupling of atoms here. These are again cobalt atoms sitting on a platinum substrate, but now we have a nearby nanostructure of cobalt. It's a cobalt nanostripe, and it is ferromagnetic. You can prove that by parking your tip above this cobalt nanostructure and measure a magnetization curve. And if you do so, that is, you measure the conductance as a function of magnetic field, you recognize that you have a very pronounced hysteresis here, a typical hysteresis loop, which you know from ferromagnets. It's a characteristic of a ferromagnet. And so we know this cobalt nanostructure is ferromagnetic. Now let's have a look to these atoms A, B, and C. And here you see the results here. And the surprise was that we also see a hysteresis loop for atom A, for atom B here, and for atom C. But there are major differences between atom B and atom A and C. If you look carefully, you see we have labeled the two different branches of the hysteresis loop here in blue and in red color. And for atom B, you see that the blue branch is above the red branch as for the cobalt nanostructure. And this is indicative again for ferromagnetic coupling. That means the magnetic moment of atom B would like to align parallel to the magnetization of this cobalt nanostripe. But for atom A and C, it's different. You see that now the red branch is above the blue branch. And this is indicative for an antiferromagnetic coupling. That means atoms A and C would like to align their magnetic moments antiparallel to this nanostructure. And moreover, you see clearly that the area enclosed by the hysteresis loop is different for atoms A, B, and C. For C, the area enclosed by the hysteresis loop is much smaller. And this gives us a measure of the magnitude, the strength of the magnetic coupling. And so by doing such measurements for many different atoms, not only for these three atoms A, B, C, but for many other atoms, you can extract the magnitude of the magnetic coupling and also the sign, which is indicative of an antiferromagnetic or ferromagnetic coupling, as a function of distance of the atoms from the cobalt nanostructure. That is, in fact, the difference between these atoms. They have a different distance from the cobalt nanostripe. And you see here very exciting results. Obviously, the strength here is such that you cannot explain these findings by assuming a classical standard magnetic dipolar interaction. The dipole interaction is much too small, and it's also always antiferromagnetic, and this is in complete controversy here to the data. So clearly what we have is an oscillatory type of interaction. It's known as an oscillatory indirect exchange interaction, or RKKY interaction. That doesn't matter. It can also be described, of course, by a formula explaining the distance dependence and a prefactor, which basically is related with a Fermi wave vector for those of you who are experts. But this is not important for the following. Important is the fact that you know now that if you bring two atoms to a distance, say, of 1.3 nanometers, you expect an antiferromagnetic coupling, very strong antiferromagnetic coupling. Also at 2.5 nanometers, you know that the coupling is antiferromagnetic. Whereas at a distance of 2 nanometers, say, or 4 nanometers, you know that the coupling is ferromagnetic. And this is very important for the following. It means that we have a roadmap to construct artificial magnets where we can predetermine the sign and also the strength of the coupling. So we can really use that knowledge to look into the direction of tailoring artificial magnets. But before I go into this direction, let me just remind you, and this has, of course, to do with the history of the city of Hamburg, where I'm located. So it was Emil Gabriel Warburg. He was born in Hamburg in 1846, and he measured actually the very, very first magnetic hysteresis loop on bulk iron, a macroscopic piece of iron. And he did this in 1880. So this was a historical measurement here in the 19th century. And you see it took basically 130 years to basically go from a magnetization curve of bulk iron with billions of atoms. You know, you have typically 10 to the power of 23 atoms in bulk iron to really a measurement of on an individual iron atom. So this is a little bit of a history here related with the city of Hamburg. And now let's move on. So we combine this knowledge now with a wonderful possibility of single atom manipulation. So that's the last method I really need to introduce. So when we have these atoms on surfaces, we can actually play around with these atoms. So we can really drag these individual atoms on surfaces, as you see here in this animation. We slide the atoms or push the atoms on the surface and then basically let them be positioned at a new place. Of course, we cannot do this with our bulky hand as shown here, but we do this with our atomically sharp probe tip as indicated here, making use of the force interaction between the front tip atom and this surface atom. And back in 2010, 13 years ago, we learned actually how to do these experiments even with magnetic tips and magnetic atoms. And you see here basically the method, and the challenge of the experiment is that the magnetic moment orientation should stay the same here when doing this atom manipulation. So it's very challenging, but the students in my lab learned about this technique, and so we could routinely build up nanostructures also with magnetic tips and magnetic atoms. And here's a first example. It's basically now a row of 7 iron atoms adsorbed on a copper 111 surface, a certain crystal orientation of copper. And of course, you would never get just by chance this kind of arrangement. This is really artificially fabricated atom by atom. And you see, we have purposely chosen a distance now of 1 nanometer because we knew from the previous experiment that this is the distance regime where we have an antiferromagnetic coupling with an antiparallel orientation. And this is why you see here different color here for the spin resolved conductance which we measure, because the iron atoms are antiferromagnetically coupled. Again, we can prove this immediately by applying a very strong external magnetic field, which is strong enough to break this indirect magnetic exchange coupling, and then all the magnetic moments are oriented along the externally applied field, and then we basically get the same orientation of magnetic moments of all the atoms. That means we get a ferromagnetic chain then of the iron atoms. And so we can play around basically and getting different kind of nanostructures with different magnetic properties. And we cannot only do this with linear chains here. We can go for all different kind of arrangements here besides linear chains, like flower-like patterns here, or other kind of arrangements, as you can see here. Or we can construct, if we wish, a circle here of iron atoms, again on a copper surface, with the same spacing between the individual iron atoms. So we can construct any kind of pattern and then again probe the magnetic state by doing these spin polarized measurements. So here in this case, it's an antiferromagnetic ring which we have built here of iron atoms. For those of you coming more from the field of chemistry, I would like to remind you that we can also have metal organic systems, molecules which are built up of metallic centers and some organic ligands. And we can actually also have then an antiferromagnetic coupling among the metal centers. And indeed, we have applied the technique equally well to these organometallic systems. So also, molecular systems can be investigated down to the atomic scale, and you can learn about magnetic couplings also in organometallic compounds, for instance, this way. Now, the final step is, and this is going now towards applications, functionalization now of these structures, that we bring now these artificially constructed patterns now together with some gates. And these gates are realized by atomic scale structures, nanostructures, for instance, of cobalt or iron. They are just 1 or 2 atomic layers high, but they are compact here in the topography, as you see. And they serve as gate electrodes. That means, as you can see here on the right-hand side, we can use them now to make a connection here by linear arrangement of atoms to such kind of structures with exactly this structure, which you can see here, which is now connected by an atomic wire here. And so we can look at the transport here in this two-gate device. We can use a third island and make the connection. It's already starting here to be built up. We can even connect here a third atomic scale wire here and have a third gate, or you can construct any kind of arrangement this way. Now, the most beautiful example, I would say, is a logic device, which we have demonstrated about 12 years ago. Alex Khachaturian in my lab was doing this experiment, and I would like to introduce a little bit in more detail the concept of a spin logic device on the atomic scale. So the idea is that the magnetization, which is pointing downward or upward, can of course be understood as a logic 0 or logic 1 state. And of course, also for the individual magnetic atoms, we basically say that a magnetic moment orientation in the upward direction refers to a logic 1 state, and a downward orientation would mean a logic 0 state. And now we can construct a logic device by having two input gates here realized by ferromagnetic islands. And now we couple antiferromagnetic spin chains like the iron chains on copper, which I introduced before, to the corners of these triangle-shaped islands. And then we basically then have a central region where these two wires come together. And then we basically have here an atom, which then defines the output state, which will sensitively depend on the input states of these two gate electrodes, as we will see. So how to construct such a device? So again, I show you first an animation to demonstrate what we actually have done. So we start with these triangular-shaped islands. We have atoms on surfaces, which are first statistically distributed. It's a random distribution, and we need to use single atom manipulation to really construct this device. So this is shown here. So you really manipulate atom by atom this way. You control the distances between the atoms until you have the final device constructed. And then, since you have magnetic atoms, of course, you can operate then this device by changing the magnetization state, say, of these triangle-shaped islands, and this will influence the magnetization state of this atom. And in the end, you can probe all that with the help of a spin-polarized scanning tunneling microscope, as indicated here. So this is the idea. To realize this, actually, you need to control the position of each individual atom. As I said, you need to make a concept which allows you to construct really with atomic scale accuracy this kind of device. It's a kind of atomic level engineering. Some of you might come from an engineering department. It's really an engineering on the atomic level, and then atomic level fabrication, which is and sometimes also automated. You can do this, of course, also in an automated way if you have basically the design concept finished. And in the following, I really show you raw data now of the real device. So here you see a corner of this magnetic island. It's a triangle-shaped cobalt island, and the color already represents the magnetization state. So bright color in this case means the magnetization of this island is upward, whereas you see we brought already two iron atoms close to this corner, and the first iron atom has its magnetic moment antipole oriented with respect to the magnetization of this island, and this is why this iron atom appears dark. Another iron atom, which is also sitting on the copper surface now, appears bright simply because its magnetic moment is antiparallel aligned to this atom. And now we bring a third atom close, and then again it's antiparallel aligned with this magnetic moment here to the second atom. Now we bring in this atom here, which is first antiferromagnetically coupled to the island. Then we bring it to this position now. Now the magnitude of the spin polarized conductance changes because of the different type of coupling now to this third atom compared to the previous position here. But you see immediately that this atom appears not as bright as the second atom. And the reason is obvious. If you look carefully, the distance between these two atoms is a little bit larger than the distances between these atoms. So you have to bring this atom a little bit closer, and then you are in this optimum antiferromagnetic coupling regime, and then you get the optimum signal strength, because now you really have the antiparallel orientation here and the maximum of the antiferromagnetic coupling. And this is what I said at the very beginning. You can monitor the outcome, say, of the physical properties of your device while constructing this device. This is this kind of online monitoring, which I mentioned at the very beginning of my talk. And then you can, of course, continue, construct this device. Here you see both islands here, the two antiferromagnetic atomic scale wires and a single atom, which is sensitively coupled to both ends of these wires here. And now what we are going to do is we change the magnetization state, first of this island and then of this island, and look what's going on now. We see that if we change the magnetization state of this island here, then also with the change of brightness here, we change the magnetization state of the first iron atom, because it always wants to be antiferromagnetically coupled to this electrode. And then basically the next atom will flip its magnetic moment orientation, and so on. So it's a kind of spin cascading effect. It's like a domino effect. If you play with dominoes, if you just push at one end, of course, one domino piece will fall after the other. And this is a kind of domino effect, which gives us possibility to transfer information from this gate electrode to this central region where we do the computation. And then we look at the state of this atom here, independence of the magnetization states of these two islands. And this is shown here. Here you see all the four permutations which are possible. Here you see both islands in bright color, meaning both magnetization directions are upward, meaning logic 1 state. Here one of the islands is dark here, and here both islands are dark, meaning we have a logic 0 state for the inputs. And you see, if you look at the state of the output atom here, we see that we only get a dark output state of this atom here if both islands are in the dark state. And this, of course, refers to a logic OR operation, so OR gate. And by changing the geometry a little bit, we have demonstrated all kind of basic logic operations. Now you might ask, how is that possible? We are at the atomic scale and we demonstrate classical Boolean logic. So it's classical Boolean logic, which is realized here on the atomic level. So it means that if we go to atomic scale dimensions, we don't necessarily have to go towards quantum logic gates. You can even scale down classical devices down to the atomic level. That's a major conclusion from this result, and this means that you have still a lot of possibilities for further downscaling classical logic devices. And here we demonstrate for the first time that you can do this even with a spin degree of freedom, which has a lot of advantages because it's much more energy efficient to operate logic devices based on the spin degree of freedom rather than on the charge flow of electrons. And also, as Richard Feynman said in his famous lecture, there's really plenty of room at the bottom. You see here basically this image scaled now to the size typically or dimensions of a transistor in 32 nanometer process technologies. So you see here the individual gates of a transistor. They appear, of course, really macroscopic compared to this tiny device. And you know, you need gate, drain, source, and so on, and more than one transistor to realize such a logic operation. So we really have shown that there is still plenty of room at the bottom for further miniaturization. Now, at the end, I would like to say that we have much more possibilities, and I know from the list of participants, some of you are working, of course, in the field of magnetic devices, and I would just like to mention that we cannot just work with parallel and antiparallel orientations of magnetic moments, but also, as indicated here, we can construct linear chains that the magnetization is rotating continuously here along the chain direction here. And this is what we call non-collinear magnetism. And you can achieve that by constructing such atom chains not on substrates like copper, but for instance, substrates like platinum. Platinum is a heavy element compared to copper. And here we have another very important interaction, which is becoming relevant, the so-called Jarzynski-Maria interaction. And this is due to spin-orbit coupling effects. So if you have large spin-orbit coupling, which you typically have in heavy elements, then this strong spin-orbit coupling effects lead to this non-collinearity, basically, of these structures. So what we have done here, or what was done actually by a master student in my group, he has built up a chain of, I think, 16 iron atoms now on this platinum surface, one by one. And if you look at the spin-polarized scanning tunneling microscope, you see now that there's a different brightness, meaning a different magnitude of a spin-polarized conductance signal. We start with low brightness, then high brightness, lower brightness, higher brightness. But now you see it's not continuing in a periodic fashion. You see when you do a line section here across this chain that you have a kind of beating pattern. And this beating pattern is due to the fact that we do not have just an antiferromagnetic chain. We have a preferred nearest neighbor antiferromagnetic coupling, but it's not exactly antiferromagnetic. We do not have rotation by 180 degrees, but by 216 degrees, which we can determine quantitatively from this data set. So we have really a spin spiral as indicated here, and this is really fascinating to the field of magnetism. You can create spin spirals in one-dimensional chains. You can create such non-collinear textures in two-dimensional thin films, which led us to the discovery of so-called magnetic skyrmions. I don't have time to go into that for the experts. Also in Singapore, some new kind of magnetic storage devices based on these magnetic skyrmions are now basically pushed forward. And this is a very exciting direction of magnetism. Moreover, it has been theoretically predicted that if you bring such spin chains in contact with a superconductor, you might get even more exciting states, so-called Majorana bound states at the ends of such spin chains. And such Majorana bound states are currently being discussed for potential applications in quantum computation, especially for achieving very robust qubits. And the background is that it was Ettore Majorana who in the mid-30s predicted a real solution to the famous Dirac equation describing relativistic fermions. And this real solution, which Majorana found, describes particles, in fact fermions, being their own antiparticles. Now, such particles have not been discovered in particle physics for sure, but we have now the possibility to achieve Majorana quasi-particles in condensed matter physics. And this was actually shown by our group based on artificially constructed spin chains on superconducting substrates, where we could see for the very first time very clear signatures of these Majorana quasi-particles at the ends of such spin chains as predicted. And here finally I show you once again that this can routinely be done. You can construct again such a chain of iron atoms one by one, now on a superconducting substrate. It's a rhenium substrate here. Rhenium is also a heavy metal, so you have also high spin-orbit coupling, which leads actually to a non-collinear ground state of this spin chain. And we can use our spin-polarized STM technique to prove that this iron chain indeed has a non-collinear structure. We can make a magnetic image here of this chain with a magnetic tip, which is out of plane sensitive and in plane sensitive. And if we look at the Fourier transform of this data set, we see basically peaks here referring to periodicities, which we can then turn into a real space picture. It's a periodicity of 4 atoms here along the chain. This is a 4-atom periodicity, meaning you get a 90-degree rotation of a magnetic moment from one atomic site to the next. It's called a 90-degree spin spiral. This can directly be extracted from the data. And if you bring this chain in contact with the superconductor, you can really find at the ends of the chain clear signatures of these Majorana quasi-particles at 0 energy. This means 0 byte bias between tip and surface here. And we have done so, of course, as a function of length of these iron nanowires, as you can see here. We did this also for many other systems like manganese atom chains on niobium. So this technique really works for all kind of combinations. This is the construction of a manganese chain with close packed atoms here on niobium substrates. Niobium is also a superconductor. And again, if you look to the electronic states, you find clear signatures of these end states. And we could even determine the band structures. So for those of you having background in solid state physics, band structures are very important. And you can reveal these band structures also with the technique of scanning tunneling spectroscopy. And we can determine basically that there's a gap here in this band structure, which is a necessary condition to get these Majorana quasi-particles. And at the moment, the top research front is really to increase this gap size to make these Majorana quasi-particles even more robust, so that we can really get very robust quantum bits, qubits for topological quantum computation. And this works then in tri-junctions, where we can have then a sequence of operations, basically, of such Majorana end states to exchange such Majorana quasi-particles and to prove one of the most famous properties of these Majorana states, namely the so-called non-abelian quantum exchange statistics. The beauty is that we can construct tri-junctions and more complex structures, as you see here, to really look at these theoretical predictions. And in the end, let me say that besides all these possibilities to now get more functionality, we can even address the switching properties here of nanoscale islands. Here you see basically that nanoscale islands, as a function of time, change their magnetization state. And we can even monitor this in real time here, the change between the two magnetization states referred to the switching between two different conductance levels, and we can monitor this in real time. And moreover, we can even probe properties by multiple tip arrangements to probe transport properties. So this gives further exciting possibilities. We can probe the dynamics of individual magnetic atoms and how this dynamics is modified by going to a 2-atom cluster, 3-atom cluster, 4-atom cluster, 5-atom cluster. And when we go to 5-atom clusters, we are already at a time scale of seconds, at least at 300 millikelvin. And this is something you can resolve very nicely, and you can make statistics of these switching events, and you can finally, and this is what we showed in this publication, look at the transition from quantum magnetic behavior to the behavior of a classical magnet. So this is a very exciting direction of research as well, to look at the transition from quantum magnetism to classical magnetism. And we can even look at the dependencies of the spin dynamics on symmetries. This is something you would not expect. Even it depends on the symmetry of the structure which we build up. A more symmetric structure like this one or this one is actually more stable than an asymmetric structure, though the number of atoms, for instance, in this structure is exactly the same as for this structure. And so you can even tune the stability of your atomic scale structure by the symmetry. And this is a completely new insight. Nobody thought about this. So you see the implications of what we do here when tailoring these magnets. We can not only tailor the couplings, but we can also tailor the dynamics. And this is, of course, extremely important for any kind of storage application, which always means you have to switch between magnetic states, and you want to do this reliably. And you also would like to have, of course, stable end states. So what I showed you in my lecture is that we can really construct new tailored nanomagnets. We can go towards atomic scale logic device. We can construct even non-collinear spin systems like spiral states in 1 dimension, and I didn't have time to go towards 2 dimensions. And we can even construct systems, hybrid systems of magnets and superconductors, where we can look at the emergence of new kind of quasar particles, like these famous Majorana quasar particles. So in the end, I would like to stress that what I reported today is, of course, a result of the hard work of many students and postdocs from many countries, like Hovan Kim from South Korea, Alexandra Palacio Morales from Spain, Alex Kachaturians from US, and so on and so on. So I really had a pleasure to work together with 300 young scientists in the past, and to bring all these techniques forward. And of course, I would like to mention that we have a unique infrastructure in Hamburg with very nice equipment where we can do all that. So this is the main building of our university, and here the campus where we do all this research in about 20 different labs of this kind. And I do hope that you have once the possibility to visit us, so that I can show you also these labs. And so I very much want to invite you, when you have a possibility, to come to our campus. This campus has really a strong history. So Wolfgang Pauli, you might know from the Pauli exclusion principle. He discovered this Pauli exclusion principle here when he was working on our campus. Ernst Ising, you might know from the famous Ising model, discovered his model during his PhD work. It was really a result of a PhD thesis at Hamburg University. Otto Stern, you might know from a famous Stern-Gerlach experiment. He discovered the anomalous magnetic moment of a proton while being in Hamburg. And Isidore Rabi, you must know from the Rabi oscillations. He was also working together with Otto Stern in Hamburg to really do these fascinating early experiments. And so it's really a campus with great history. And I really invite you to come to Hamburg, hopefully in the future, to have a look at the campus, but also look to the city. And so with that, I would like to end my lecture, and I thank you very much for your kind attention.
Thank you, Professor Wiesendanger, for the stimulating talk. I think we can start the Q&A session now. So a couple of instructions for the participants. So you can use the Q&A feature at the bottom panel of your Zoom screen to ask your question. You can simply type your question there, and I can read your question for you. In case, yeah, I suggest that you don't use the chat feature for asking questions. Also, in case you prefer to ask the question directly, you can use the raise hand feature, and we will allow you microphone access, and then you can ask your question directly. So I think we already have a couple of questions from the participants. So maybe I can read the questions for you, Prof. So
Yeah, that would be
first
nice.
question, okay. So the first question we have from Ragesh. The question is as follows. Can STM be used to correlate surface properties in natural biomaterials, non-metallic in nature, mostly carbon-based?
That's an exciting question. So the scanning tailoring microscope is just one example of a whole family of scanning probe techniques. So STM is wonderful to probe electronic properties and also magnetic properties, as I indicated, but has a drawback that it cannot be applied to insulating materials. And in most cases, biological systems, of course, cannot be really addressed with and probed with STM techniques. But there is this technique of atomic force microscopy, which measures force interactions. And atomic force microscopy can be applied also to biomolecules, also to larger biomolecular systems. And the beauty is that you cannot do this just in vacuum. Atomic force microscopy can also be applied in liquid environments, so in natural environments of biomolecules. And there are experts, and maybe you might want to invite one of these experts in the future who have developed further this atomic or scanning force microscopy technique, particularly in view towards applications of biomolecules under natural conditions. That means in liquid environments. For instance, in Kanazawa, there's a colleague, a Japanese colleague, who is really at the forefront of the developments of the applications of this atomic force microscopy technique to biomolecules. So the clear answer is yes, you can do it, and you can even go down to molecular scale dimensions to probe also structure function relationships of biomolecules, really down to extremely small length scales.
Okay, thank you, Prof. So we have another question from Yugia. The question is, how do you ensure that the atoms are fixed at the designated positions during the operation of the device?
That's a very exciting question. So the atoms on the surfaces have always, say, some preferred position which is related to the surface potential. So there are spots on the surface where the atoms would like to absorb because there's an energy minimum basically at these particular locations. Typically, these are the hollow sites. So if you just imagine such an atomic scale structure of your surface, there are always holes, yeah, as you would basically have a two-dimensional arrangement, say, of spheres. You also have, of course, always some holes between these spheres. When you have three spheres together in the center, of course, you have some hole positions, and these are the so-called hollow sites. So the atoms would like to stick to these hollow sites, and if the temperature is low enough, the atoms will not diffuse on the surface. However, of course, if you would increase the temperature now towards room temperature, then the atoms will not stay stable in position, at least not for metal surfaces. For semiconductors, it's different. For semiconductors, you can demonstrate single atom manipulation even at room temperature. Why is this? For semiconductors, you have very strong covalent forces, as you might know. So these covalent forces are much stronger than the weaker interactions in metallic systems if you have atoms on a metal substrate. And so it's basically the bond strength which determines the temperature scale where you have to do these experiments. But you can also construct such atomic scale devices based on semiconductor substrates, even up to room temperature in principle.
Okay, thank you, Prof. I think Adil wants to ask a question directly. Adil, would you like to unmute yourself and ask your question?
Yeah, sure. Thank you for the wonderful lecture. Coming from more of a mechanical engineering angle, I noticed that your visualizations of the SPSTM readings seem to have a spatial resolution which is much smaller than the size of a single iron atom's field in the visualization. As the tip of the microscope is taking a point measurement, I assume this high spatial resolution means the tip must have been actuated on the X and Y axis in such small increments of a fraction of a nanometer. So how is this achieved mechanically?
This is an extremely good question. So I mentioned that piezoelectric elements are used to basically make the motion of the tip. Yeah, you have either a triport scanner or this tube scanner from piezoelectric material. And of course, you are perfectly right. The piezoelectric material, like any other material, is made up of individual atoms. And so one could ask, I mean, is it possible to achieve subatomic accuracy with a piezoelectric drive, though, of course, the material is made up of individual atoms? That was not clear before this wonderful instrument was actually developed. The experiments showed, in fact, that you can have this subatomic accuracy. So that means usually you have a linear relation between the applied voltage on your metal electrodes on these piezoelectric drives. And when you apply very small voltage changes on the order of a few millivolts, you can really get down to changes in elongation of these piezoelectric elements, which are even down to the subatomic scale. Now, how do you measure this? This is measured by the tunneling current between the tip and the surface. This tunneling current is very sensitive to distance changes because the tunneling current is exponentially dependent on distance. That means if you have a variation only of 1 angstrom, you get a 1 order of magnitude change in the current, a huge change of current when only changing distance of 1 angstrom, which is already a fraction of the diameter of an individual atom. And only with this extreme sensitivity of the tunneling current, one could show that these piezoelectric drives allow for subatomic accuracy in positioning of the tip, both in the vertical direction, that means along the surface normal, as well as during the scanning. So also the lateral positioning can be done with subatomic accuracy. And that was not clear before the invention of the scanning tunneling microscope. It was really a result of this extremely sensitive measurement. And that has implication because you are coming from the engineering side, that is also used these days actually for atomic level fabrication. In Japan, I know there are fabs which usually have been working, say, on microsystems and microscales. But nowadays, we are really at the level where we can do any kind of manipulation with subatomic accuracy due to these wonderful techniques. This goes well beyond just doing scanning tunneling microscopy. It's really a new way to do engineering with subatomic level accuracy.
Thank you for your answer. One more thing. So do you know which software is used to do 3D visualizations, which you have shown?
The software is are various kinds of commercial softwares. Sometimes it's modified by students. If you are interested in that, you can just write me an email, then I can give you 2-3 examples. It's commercial software, more or less, and many times it even comes together with the data acquisition software. So it's not really so specific. You can find this software together with other kind of microscope techniques like electron microscopy or any other kind of microscopy technique. It's really not so special. You might refer maybe to the animations. Of course, the animations made use of more special software. It was not based on a single software package. The students over the time used various software packages. So if you are really interested in that, you can write me an email, then I can send you some information about that.
Thank you. That's all from my end.
Mm-hmm.
Okay, thanks, Adil. We also have a question from Noah. The question is, how time intensive is it on a real-time basis to actually manipulate the atoms one by one to create the demonstrated OR gate device? Also, how easily reproducible are these very precise manipulations, considering the sensitivity of these measurements to background noise?
Very good. So the reproducibility is really great. I mean, we can always reproduce the construction of these structures, but it's indeed a question. I mean, how many atoms can we manipulate in a certain amount of time? So usually if it is just for research purposes, we manipulate, say, up to 200 or 300 atoms. In the future, of course, you would like to do it on an automated basis if you really would like to make use of that for technology. And it depends a lot on the special combination of atoms and especially substrates, how easy it is. So on copper surfaces, for instance, it's very, very fast. You can really manipulate hundreds of atoms a day or so, and it's really fast and very reliable. So if you have surfaces like niobium, it's more complicated, and there are indeed some surfaces like lead surfaces where it is almost impossible to manipulate atoms, and that has to do with a very special surface potential of these lead surfaces. So it really depends on the special combination of the atoms and the substrates, how fast it can be, but in all cases it is very reliable once you have such an atomically sharp probe tip. So sometimes the students have to work a little bit to really get the optimum tip, but once you have this tip available, you can very reproducibly manipulate the atoms and construct really large arrays. Today I showed, I think, arrays up to 50 atoms or so, but we have constructed really large scale arrays of many hundred of atoms, and each atom has its really specified position, and so that is not really an issue. And in the end, of course, we want to demonstrate the feasibility of these kind of devices. Of course, if you really would like to go towards manufacturing, then you have to think of more issues, of course, but in the end, we think that we might want to fabricate really just the internal part of these devices, which can be used, for instance, as qubits. And if we can construct, for instance, 100 qubits based on these Majorana states, then it would be wonderful. And to construct 100 of these Majorana qubits is absolutely feasible with the kind of techniques currently available, and also the reproducibility is really sufficient to construct 100 qubits, which are absolutely exactly the same on the atomic level.
Okay. Thank you, Prof. So next, Andre would like to know what are the main limitations to scale up this technology and produce working devices such as logical devices, memories, etc.
Yeah, that's a good question. So, of course, the goal of research is always to be well ahead of the industrial development. So, of course, as you know from the history of a transistor, if you look to the very first version of a transistor compared to what we have currently in integrated circuits, of course, you cannot compare this at all. So nobody knows in which direction it will go. But most important, what you have learned in my lecture is that by going down to these atomic scales, we can really learn about the fundamental interactions which are important to tailor the properties of materials and devices on this length scale. And this helps a lot. It helped, for instance, in the discovery of so-called magnetic skyrmions. Just 10 years ago, we discovered individual chiral magnetic skyrmions, and nowadays, like a group actually in Singapore, develops now already first skyrmion-based MRAMs, magnetic random access memories. They are not yet on the market. You know, MRAM devices are on the market, but now people are working towards using skyrmions in these kind of devices already 10 years after the discovery. So nobody knows how fast it will go, but it's always important to stay ahead in the research you are doing, and at least then have the technologies ready once the industry is really in a position to really take over these kind of technologies and this kind of knowledge. But I know, for instance, also of very nice activities in Sydney in Professor Michel Simmons' group. They are, for instance, producing atomic scale transistors already. And so nobody knows when you have an atomic scale transistor on the market. But it's important that we as scientists prepare for these technologies in the future by doing very well-defined experiments at very small length scales, understand what we are doing, and basically provide the basis of future technological directions.
Okay, thank you, Prof. So next we have a question from Xiu Xiang. So Xiu Xiang would like to know what is the connection between atomic spin and lattice vibration?
Ah, very good. So lattice vibrations have to do with the motion of the atoms around their equilibrium positions. So, of course, in a crystal, the atoms, of course, have their equilibrium positions, which are governed, of course, by the interactions between the atoms. And vibrational motions are basically motions around these equilibrium positions. And you get basically higher and higher elongations around these equilibrium positions if you, for instance, enhance temperature. So in a quantum picture, you might speak of phonons, which are elementary excitations of these lattice vibrations. And the higher the temperature is, the more phonons you can excite. The spin degree of freedom is something completely different. So the spin degree of freedom, of course, has to do with the electronic configuration of the individual atoms building up this crystal. And so you need an open electronic shell to have uncompensated spins, of course, and then you can create some magnetic moment, of course, on each individual side. And you can get a magnetic material if the magnetic interactions allow for some preferred orientation, for instance, of the magnetic moments, either parallel or antiparallel as in a ferromagnet or antiferromagnet. But please note, we have basically three independent degrees of freedom. We have the vibrations, which are basically related with the motion, with the positional degrees of freedom of the atoms. we have the electronic degrees of freedom, of course, related with the electronic charges, and we have the spin degree of freedom, and all of that is independent. So the spin is a completely independent property from the charge, and it's a completely independent property, of course, from the motional degree, the positional degree of freedom. And basically condensed matter physics is about the interaction of all these degrees of freedom. This is why condensed matter physics is so rich, because you can have a lot of phenomena where these different degrees of freedom interact with one another. So indeed, there are also some researchers studying spin-phonon coupling, the coupling of the spin degree with lattice vibrations, but this is a different field.
Okay, thank you, Prof. Also, we have a slightly non-technical question from Naveed. So it seems that Naveed is an undergraduate student interested in nanomaterials and nanoscience. And the question, so are there any suggestions you may have for someone who wants to succeed in this domain?
Yeah, I think I should say generally that it is very important also at the undergraduate level, at a very early stage, to look to new directions of research, not following, say, lines of research which are already well established, but to look for new topics coming up of great excitement. So I can just tell you from my own experience when I started with my studies in physics at the University of Basel, as you mentioned at the beginning. I started actually because I wanted to do research in particle physics. However, then after 2 or 3 years of my studies, I learned about these fascinating new developments in the field of the development of a scanning tunneling microscope by Gert Binnig and Heinrich Rohrer. So Gert Binnig gave a colloquium actually at our place, and then I completely changed my mind, and I saw the potential of a technique which can address atomic scale structures. Yeah, and this is important, to be open-minded towards new directions and to look for new possibilities. So at the moment, I would say, when referring to solid state physics or condensed matter physics, you know that the field of electronics is very well advanced based on say, semiconductor technology, and this is based on the fact that a lot of researchers studied well-defined semiconductor heterostructure systems from the 70s, 80s of the previous century. Then later on, starting with the 90s, you know that magnetic materials became into the focus of research, where the field of spintronics came up, that is electronics using the spin degree of freedom and basically developing new devices, making use of magnetic materials. Nowadays, we have a great challenge, especially in the field of superconductivity, to advance superconducting devices and also devices based on hybrid systems of superconductors and semiconductors, or superconductors and magnetic materials. And especially the application of such devices would, of course, explode if you would have superconductors which are superconducting at room temperature. So real great challenge is, of course, to develop materials which hopefully are stably superconducting at temperatures well above room temperature, and also already to develop devices which can hopefully be used in the future based on this dissipation-less flow of currents as you have in superconductors. And this would also advance electronics in generally, and will also contribute, of course, to energy-serving technology. So this is a very interesting and exciting direction of research. And especially atomic scale microscopy techniques and technologies can help to basically develop based on a very fundamental knowledge of the interactions to develop better material systems, also better superconductors, hopefully. And this is also a very important direction of our research, to look into new directions of novel superconductors based on outstanding properties, which we can basically address and visualize down to atomic scales.
Thank you very much, Professor. So I think we don't have any more questions from the audience. Maybe would any of the co-hosts like to ask any questions?
Hey, Professor, thank you for the talk. So I had a general question, like what could be the reason behind the antiferromagnetic behavior of iron monolayers?
That's a very good question. Usually in bulk iron, you know that the interactions are such that they prefer a parallel alignment of magnetic moments. However, most important, if you go to atomic scales, the properties of materials can change drastically. So that has to do, on one hand, with the fact that you really have a hybrid system of an iron layer and a substrate. So you have also interactions at the interface between your magnetic thin film and the substrate, which play a crucial role. And these interfacial interactions, of course, can modify the fundamental interaction properties like exchange interactions. And this is indeed the case for this example of iron monolayer on this tungsten 001 substrate, that by looking into the theory then of the system, calculating from ab initio the electronic states, we found out that it is really the properties of this special interface which stabilize actually the antiferromagnetic ground state. Moreover, there are examples, for instance, of iron selenium monolayers on a strontium titanate substrate, where you find outstanding superconducting properties of this iron selenium layer. This is also referring to the previous question. So that one can go into new directions of superconductivity by just going to the single atom limit, or at least atomic layer limit. And that makes this field so rich, and this is the motivation to go to the nanoscale, that even with the same material iron, you can modify the properties. You can modify magnetic properties, electronic properties, superconducting properties by just going to lower dimensions, and also to profit from new properties which result from the interaction of these nanoscale systems with the substrate.
Thank you, Prof. Thank you.
Okay. Shakti, you are muted actually. Seems you're saying something.
Yeah, I was saying, yeah, can you hear me now?
Yeah.
Yeah, I think we can wrap up considering the time.
Sure. Okay.
Yeah.
Yeah. All right. So let's again thank Professor Roland for this stimulating talk and for taking his time to answer all our questions. And thank you all for your participation. I think you all will see a QR code at the end of this session, which is for a survey. And I think also people who want seminar endorsement can refer to scan the QR code.
Thank you very much again for your interest, and I really enjoyed the discussion. And as I said, whenever you have an opportunity, please contact me so that you might have an opportunity to visit Hamburg in the future. And yeah, whenever you have more questions, please do not hesitate to contact me by email or any other means. Yeah.
Thank you.
Thank you very much, Prof. Roland.